Tony, do you still visit Singapore?
Uh, I haven't visited for several years now.
Tony,
Let's see, the
do you
last
still
time was in
visit
January of
Singapore?
2017, I think.
Okay.
And that
What
was
did?
when I got diagnosed with prostate cancer, and I had to terminate my visit rather quickly at
Okay.
that point because I needed to get some treatment for my prostate cancer.
Okay.
Um, so uh, so I have not been back since then. But I keep in touch with various people in Singapore.
Mm.
I have not been back since then.
Yeah.
I keep in touch with various people in Singapore.
Mm.
Have not been back since then.
Yeah.
I keep in touch with various people in Singapore.
Mm.
Have not been back since then.
Yeah.
I keep in touch with various people in Singapore.
Ada, ada.
Yeah. Um. Uh, yeah. I think the time that you go to Singapore in 2017 is they have GYSS, right? The
Yes, that's right. Yes,
yeah.
for the
The
last
time
few
that you go
years,
to
um,
Singapore in
so I think probably
2017 is
2014, 15, 16,
they have
17,
GYSS,
I
right?
was regular
The
party to the GYSS. For the last few
time that you go
years,
to
um,
Singapore in
I think probably
2017 is
2014, 15, 16,
they have
17,
GYSS,
I
right?
was regular
The
party to the GYSS. For the last few
time that you
years,
go to
um,
Singapore in
I think probably 2014, 15, 16, 17, I was regular party to the GYSS. For the last few years, um, I think probably 2014, 15, 16, 17, I was regular party to the GYSS.
So we wait for Prabha. Okay, now Prabha.
All right. Hi, morning, Tony. Oh, sorry,
Morning.
evening, Tony.
Yes, good morning to you. Yes,
So we wait
Yeah,
for
yes,
Prabha.
I'm
Okay.
sure good.
I'll be moderating this morning. Oh, sorry, evening, Tony. All fine? Good?
Yes, good morning to you. Yes, yeah, yes, I'm sure good.
I'll be moderating this morning. Oh, sorry, evening, Tony. All fine? Good? I didn't hear anything there. Okay. If I may ask, Tony, are you still an active faculty member?
Well, technically, formally, I'm retired from the University of Illinois. I do try to keep in touch with what's going on. I now am carrying a on a small research program with one of my faculty colleagues and a couple of students. Um, but it's very informal. I'm not the informal advisor or anything like that.
You mean informal as in just the research portion, or informal as in you do not have postgraduates under your wing?
Not formally, no. As I say, I am informally advising a couple of, well, actually one graduate student and one undergraduate on this little research project.
Okay,
Um,
okay. But un, 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 unlimited access to the university.
oh yeah, yeah, yes, no problem about that. Yeah,
That's nice. That's nice.
yeah.
Unlimited access to the university.
Oh yeah, yeah, yes, no problem about that.
That's nice. That's nice. Oops, that's a bit of echo. Delayed.
Uh, yes.
Echo, delayed.
Is it?
Oops, that's a bit of echo. Delayed. Echo, delayed. Okay, good morning, everyone. Um, Salam sejahtera, salam pagi, and a very good morning to all gathered here virtually. Um, we are here for International STEM and Innovation Colloquia Series 21. Thank you too again to Drs. Nazri Halif and Sharifan Faiza. Thank you too to UNIMAP Vice Chancellor Prof. Zaliman Sauli and Deputy Vice Chancellor of Research and Innovation Prof. Rizal Fandi, their respective officers, and broadcast control team here led by Mr. Shahrizan. For hosting this event, as well as IEEE Sensor and Nanotechnology Council Malaysia for collaborating in this ISICS session. I'm Prabha, the moderator for this ISICS Series 21. Before we begin, as is normal, I would like to introduce our esteemed speaker for this ISICS Series 21, a very familiar figure for UNIMAP, Sir Anthony Leggett. We wish, we, we wish you a very good evening, Sir Anthony.
Hi. Morning to you.
So Anthony J. Leggett, the John D. and Catherine T. MacArthur Professor and Professor at the Center for Advanced Study Professor of Physics, has been a faculty member at Illinois since 1983. He is widely recognized as a world leader in the theory of low temperature physics, and his pioneering work on superfluidity was recognized by the 2003 Nobel Prize in Physics. He's a member of the National Academy of Sciences, the American Philosophical Society, the American Academy of Arts and Sciences, Indian Academy of Sciences as a foreign member, and is a fellow of the Royal Society, United Kingdom, and the American Physical Society and the American Institute of Physics. He is also an honorary member of the Institute of Physics, United Kingdom. He was knighted by Queen Elizabeth. He is also an honorary member of the Institute of Physics, United Kingdom. He was knighted by Queen Elizabeth II in 2004 for services to physics. Um, and in 2013, he was given an honorary doctorate of science by the royalty in Perlis in conjunction with UNIMAP. Um, Professor Leggett has shaped the theoretical understanding of normal and superfluid helium liquids and other strongly coupled superfluids. He set directions for research in the quantum physics of macroscopic dissipative systems and use of condensed systems to test the foundations of quantum mechanics. His research interests lie mainly within the fields of theoretical condensed matter physics and the foundations of quantum mechanics. He has been particularly interested in the possibility of using special condensed matter systems, such as Josephson devices, to test the validity of the extrapolation of the quantum formalism to the macroscopic level. This interest has led to a considerable amount of technical work on the application of quantum mechanics to collective variables, and in particular on ways of incorporating dissipation into the calculations. He is also interested in the theory of superfluid liquid 3 helium, especially under extreme non-equilibrium conditions, in high temperature superconductivity, in low temperature properties of glasses, and in topological quantum computing, particularly particularly in the uh, P plus IP Fermi superfluids.
Okay.
Today, Sir Anthony will talk about the serendipitous route to the Nobel Prize. Question and answers, I hope, are welcome during. You are welcome to um, interrupt halfway if you wish to. Otherwise, we will wait for the. Okay, okay. In that case, we will stop. We will stop. We will let Prof. Tony talk first, and then we'll go for Q&A at the end. Okay. Okay. So Tony, the floor is yours.
Okay, thank you. Well, good morning, everyone. I would like in this talk um, to I should say, first of all, it's a great pleasure to be back in contact with UNIMAP, where I had a very pleasant visit and received an honorary degree in 2013. In this talk, I would like to tell you about some serendipities, that is, strokes of unexpected strokes of luck, which were essential in the process which led me to eventually receive the Nobel Prize in physics. So, next slide, please. Okay. So let's go back for a moment to 1957 and think about the general situation in parts of low temperature physics in those days. Well, the big development in 1957 was the theory of superconductivity proposed by Bardeen, Cooper, and Schrieffer at the University of Illinois in Urbana-Champaign, which is where I'm now working, but was not at that time working. And according to this theory goes something like this. According to the principles of quantum mechanics, then elementary particles can be classified into two types. There are fermions, which are very xenophobic, and bosons, which are very gregarious. So they behave in completely opposite ways. Under appropriate conditions, bosons will display the phenomenon of Bose-Einstein condensation, or BEC. That means that they must all behave in exactly the same way, like a platoon of well-drilled soldiers. Now, the electrons in metals are fermions, so they can't undergo BEC directly. Please stay on the last slide for a moment. Please go back a moment. Yeah, thank you. So the electrons can't undergo BEC directly. However, two fermions basically make up one boson. So if electrons can form pairs, you might think of them as sort of dielectronic molecules, then the pairs can undergo Bose condensation, and then they are predicted to show superconductivity. In order to form these molecules, the electrons must experience an effective attraction. So that's a very basic ideas of the so-called BCS theory of superconductivity, which was developed in 1957. There was a second major development in the mid-50s, and that was the Landau theory of Fermi liquids. This basically considered a set of fermions with strong, mostly repulsive interactions. And it showed basically that they behave very much like a gas of non-interacting fermions, with a few slight modifications. Next slide, please. Next slide, please. Can I have the next slide, please? Yeah, thank you. Thank you. So, in fact, liquid helium-3 is a system of fermions with strong interactions, which are thought to be mostly repulsive, but partially attractive. And therefore, around 1964, which was when I first became seriously interested in the subject, the theoretical picture went something like this. The normal state of liquid helium-3 was thought to be well described by Landau Fermi liquid theory, and that did seem to give good agreement with experiment. But because part of the interaction is attractive, the expectation was that these fermions would form Cooper pairs, like the electrons in a superconductor, but with one important difference. In a superconductor, the internal state of the pairs, that is the dielectronic molecules, is isotropic. The spins are opposed so as to give total spin zero, and there is no relative rotation. By contrast, it was conjectured that in liquid helium-3, if a Cooper paired phase formed, then it might be anisotropic. The spins could possibly be parallel, and you might have a non-zero relative angular motion. And there was quite a bit of theory along those lines. Since the helium-3 atoms are electrically neutral, if Cooper pairs are formed, the system will not be superconducting. For that, it will need to be charged, which is not. But it should be the neutral analog. That is, it should be superfluid. So people started conjecturing about a superfluid phase of liquid helium-3. But it was not, at that time, in 1964, it was not found experimentally. Next slide, please. Next slide, please. Thank you. Okay, so now my own personal history. I did my doctoral work with Dr. Ha in Oxford, and part of it was on the normal phase of helium-3. Then I went to the University of Illinois at Urbana-Champaign as a postdoc under the formal supervision of David Pines. And my first work, which I did at UIUC, was on superfluid helium-3. What I did was to put together the work of Landau on the strongly repulsive interactions in the system and the BCS theory of Cooper pair formation. Now, people had looked at the combination of those two theories, but only at zero temperature. And at zero temperature, it was very boring. It simply meant that you just multiplied the properties by a certain factor, which was not terribly interesting. However, when I came to look at what happened at non-zero temperature, things became very interesting. The temperature dependence of various quantities, like the spin susceptibility, chi, and the superfluid density, rho sub s, that turned out to be interestingly different from simple BCS theory. Now, I was very excited about this, and I published a couple of papers. I gave various conference talks, which are quite well regarded, and this was really a tremendous shot of adrenaline for me. It encouraged me to go on in physics. Otherwise, I think I might well have quit physics and just become a high school teacher or something of the kind. But this was quite exciting. So that was actually what I call serendipity number one, because what I didn't actually know at the time was that these, um, although I had found these results in an independent and what I thought was a very nice way, they were not in fact entirely original. Fuldy and Farrell had derived my result essentially for the spin susceptibility, and Larkin had a paper which arguably could be said to have derived the expression for the superfluid density. And I really think it's just as well I didn't know that, because had I done so, it would have been much less exciting. And I probably, well, I might well have quit physics and gone into high school teaching at that time. But anyway, in fact, I didn't know, and so I went on. In my second postdoctoral year, I worked with Professor Takeo Matsubara, or at least I worked in his group, in Kyoto in Japan. And among other things, I worked on two-band superconductors. And that was something, um, that was two-band superconductors were thought to exist, for example, in niobium. And two bands means that the Fermi energy intersects more than one band. And it turns out that these superconductors, if they exist, have quite interesting properties. So I did some work on that and published a couple of papers, but the moment I published the papers, the experimentalists changed their mind and decided that two-band superconductors did not, in fact, really exist. So that at the time seemed a waste of time. Anyway, that's what I did in Kyoto. Uh, I had another postdoc year moving around to various places in 1966, and then in 1967 I went to work at the University of Sussex in the UK on various topics in low temperature physics, including normal liquid helium-3. And in the process of that work, I made contact with an experimentalist named Bob Richardson at Cornell University in the US. In fact, I did the theory on an experiment which he was doing at the time. Neither he didn't know about the theory, I didn't know about the experiment, but when we compared notes, it turned out that the theory did describe the experiments rather well, actually. No, but no, please stay on the last slide, please. Thank you. Um, but I was getting more and more interested in the foundations of quantum mechanics. And by the early summer of 1972, I had more or less made a conscious decision that I was going to stop doing low temperature physics and just concentrate my time, the time I had for research, entirely on the foundations of quantum mechanics. Then something important happened. In the early summer of 1972, Bob Richardson, that's the experimentalist I had exchanged ideas with at Cornell, he actually visited Sussex, where I was working I was employed at the time. Now, the reason he visited Sussex had nothing to do with physics. It was because his wife was the was a very good friend of the wife of one of my colleagues at Sussex. And that was really the only reason that they visited there. So it was a complete accident. At the time, at the time when he was just about to visit, I was actually on a holiday, a mountaineering holiday in Scotland. For some reason, I don't remember, some trivial matter, but I had to make a phone call back to the University of Sussex. Had it not been for this trivial matter, I would have never bothered to call. But anyway, when I called, then whoever answered the phone told me that Bob Richardson was going to be visiting Sussex, and if I was there, would like to talk to me. Well, I had to make up my mind because I was really enjoying my um, holiday in Scotland, and in order to get back to Sussex in time to meet Bob Richardson, I would have to go back a day early and cut my holiday short. And so I was basically tossing a coin as to whether I should come back or not. And in fact, I think on the day in question it rained. It often does rain in Scotland, and um, so that tipped the balance in favour of going back to Sussex. So I went back to Sussex. I met Bob Richardson, and what he told me that day permanently changed my career in physics. And I'll now try to describe what it was that he told me. Okay, next slide, please. Okay, so this is getting into the more technical. The Cornell group, of which Bob Richardson was the leader, had been doing experiments on nuclear magnetic resonance in helium-3. Nuclear magnetic resonance, what you do is you apply a magnetic field, H, in the vertical direction, and the nuclear spins of the nuclei, then do what is called precessing. They rotate around the axis of the field. And the rate at which they precess is, is some constant gamma, it's called the gyromagnetic ratio, times the field. In helium-3, gamma is a known quantity. It's roughly 3 kilohertz per Gauss. So given the rate of precession, at first sight at least, will measure the magnetic field. So how do you measure the rate of precession? Well, you apply an oscillating RF field transverse to the external field, and you find that that field is strongly absorbed when its frequency matches the frequency of precession. When that happens, the spins can absorb a large amount of energy from the oscillating field. So that's a very standard technique that had been developed for many years in various substances. And so they were doing it in liquid helium-3. Next slide, please. And they were working at very low temperatures, below about 3 milledegrees. That's about 100,000th of room temperature. In this figure, temperature is decreasing to the right. So in the normal phase, what they found was that the frequency of precession was indeed given by this gamma, gyromagnetic ratio, times the external field. That's nothing at all surprising. It's exactly what you'd expect. However, it turned out that there was what looked like a phase transition into what seemed to be a different phase, which nowadays is called the A phase, which takes place at about 2.8 milledegrees. And once you get into the A phase, then the resonance frequency starts increasing. The resonance still is very sharp. That's very interesting point. The resonance remains very sharp, but the frequency goes up, and it continues to go up as long as you stay in the A phase. Then there's a second transition at a lower temperature, in which you go into what is nowadays called the B phase. And then when you do that, the resonance frequency apparently drops back to the value it had in the normal phase. And what is really interesting is that the in the A phase, the frequency shift is not proportional to the external field. Rather, you have what I call a Pythagorean formula. The resonance frequency is the constant gamma times the square root of the external field squared plus the internal field squared. So what's going on? What's interesting is that although people were speculating that this had something to do with superfluidity, Cooper pairing, and therefore superfluidity, no one had actually bothered to think about NMR, about how NMR would behave in the Cooper paired phase. So we basically had to come at it from scratch. What I call serendipity number 4. Almost all my colleagues, my theoretical colleagues, who tried to think about this problem, knew standard NMR theory as developed, for example, in the standard textbooks by Abraham and people like that. I didn't. I did not know standard NMR theory. And therefore, I had to really approach the problem completely from scratch. And that was, I think, an amazing advantage, because all these people who did know standard theory went off in the wrong direction and did not, in fact, in the end, manage to explain what was going on. Next slide, please. What is it? Well, it turns out that this is sorry, stop. Well, what are the experiments? Well, in the A phase, as we already saw, the precession frequency nu, it's larger than the value in the normal phase and given by this so-called Pythagorean formula, the square root formula. And what's the interpretation of that? Well, the obvious interpretation is that the external field is in this direction, and then you have a field perpendicular to this in the transverse direction. And so you get a total field, which is the vector sum of those two. That's the dashed line in the slide. And that total field is then given by the Pythagorean formula, and you might expect that the nuclear spins would then precess around this total field and not around the external field. I was like, so. Next slide, please. But there was a problem. The only possible origin of the internal field, this transverse field, is the other nuclear spins. But the spin-spin interaction, the magnetic moment of a nuclear spin is very tiny, and moreover the field is falling off as r⁻3. And therefore, at the closest distance of approach of two atoms to one another, the maximum value of the field of one nuclear spin on another is less than 1 Gauss. But the experimental value of this internal field, which we had to postulate, is something like 30 Gauss. So that just didn't work out. Something very, very puzzling was going on. And my first thought, actually, was that, well, maybe this is the first evidence for the breakdown of quantum mechanics. After all, we were going into a regime which no one had really explored before, not just at very low temperatures, but also very high densities and strong interactions at these temperatures. And so it was guaranteed that quantum mechanics would still be working. So I seriously began to consider that a possibility. If you want to, so the first goal I set myself was to prove that if these experiments were right, then it had to show a fundamental breakdown either of quantum mechanics or of statistical mechanics. Well, how do you show such a general conclusion? The only way to do it, or the only way I knew how to do it, is by using rigorous results. For example, sums. And so I investigated the results on applying sum rules to this problem. Next slide, please. Next slide, please. Yeah. Okay. And so I did. But what I found was not what I expected. I found you could explain things within the framework of standard quantum mechanics and standard statistical mechanics, but it was more complicated than it looked. First of all, the simple classical argument about a transverse internal field was too naive. There was really no such thing as this transverse internal field. Nevertheless, it turned out that one could predict this Pythagorean formula, provided that the internal field, or the field H0, was proportional to the average value of the nuclear dipole interaction energy. That is the energy of interaction between two nuclear dipoles. Now, we know the experimental value of H0. As I said, it's more than 30 Gauss. So that meant that the value of the dipole energy, nuclear dipole-dipole interaction, had to be of the order of 10 to the minus 3 ergs per cubic centimeter. Now, that doesn't sound a lot, but in fact, it's actually huge by low temperature standards. Next slide, please. So, in fact, why is that? Is that a problem? Well, you can think of the nuclear spins as like little magnets. And so you imagine what happens if you put two little magnets side by side. You can actually do this experiment in the laboratory. It turns out they don't like that. It's bad in the sense that it costs you a lot of energy. It's much better to put them end to end, like so. That's good. So far, so good. The trouble is the energy difference between good and bad orientations per pair, the energy difference per pair is only less than 10 to the minus 7K. Whereas the thermal energy at the temperatures we're talking about is of the order of 1 millik, that's 10 to the minus 3K. So that should mean, at first sight, that the thermal preference for good orientation over bad is only the ratio, delta E over E thermal, that is less than 10 to the minus 4. And that in turn would mean that the resulting value of the nuclear dipole-dipole interaction energy is much too small to fit experiment. And in turn would mean that the resulting value of the nuclear dipole-dipole interaction energy is much too large to fit experiment. And in turn would mean that the resulting value of the nuclear dipole-dipole June of 1972, turning this problem over in my mind. And I finally came to what I thought was a solution to that problem. And that's on the next slide. So next slide, please. Yeah. And I called that the idea that I came up with spontaneously broken spin-orbit symmetry, or SBSOS for short. And to explain it, the easiest thing is to make an analogy with ferromagnetism. So imagine what happens in a ferromagnet. In a ferromagnet, if you apply an external field, then the spins would rather orient themselves along the field rather than opposite to it. In other words, along the field is good, against it is bad. But the difference in energy for a spin is some delta E, which is really pretty small. And so above the Fourier temperature, in the so-called paramagnetic phase, the spins basically behave independently, which means that the thermal energy, E sub thermal, competes with delta E, and the polarization is only delta E divided by E thermal, which turns out to be very much less than 1. So you don't get any substantial degree of polarization. Okay, now let's make an analogy with liquid helium-3 in the normal phase. Again, now one's not talking about the energy of single spins, but rather the energy of pairs of nuclear spins. So for a given pair, the good orientation is this, and the bad orientation is this. But again, the difference in energy per pair, as we already saw, that's less than 10 to the minus 7 K. And therefore, in the normal phase, where the pairs behave independently, the thermal energy competes with delta E. The polarization, that is the preference for the good orientation over the bad one, is only of the order of the ratio of delta E to E thermal, which is much less than 1. But now, let's go on to the paramagnetic phase. Next slide, please. Next slide, please. Okay, so now let's imagine we're below the critical temperature. And now the strong forces, which have nothing to do with the external field, right? The exchange forces have to do with the Coulomb force and the fact that when you exchange two spins, you have to get a minus sign and so forth. What that does is to constrain all the spins, or most of them, to lie parallel. In other words, the system has to choose now between having all your spins up, or having all which is a good orientation, or having them all down, which is a bad orientation. And now what is the difference in energy? It's not delta E, it's rather n times delta E, which is much greater than the thermal energy. And therefore, the polarization can be of order 1, and therefore, as we all know, below the critical temperature, we find that the spins tend to all line up in the direction of the external field. And even a very small field can orient them in that way. Now, let's try to make an analogy in helium-3. In the A phase, let's assume that the strong forces, that is the kinetic energy, the van der Waals energy, or so forth, for some reason or other, constrain all the pairs to behave in the same way. Then either all of them must be in the good orientation, or they must be all in the bad orientation. And notice, incidentally, that has nothing to do, that constraint, that they must all behave in the same way, has nothing directly to do with the dipole force. Okay? It's completely due to other kinds of forces, like kinetic energy and van der Waals. And now, the difference between the good and bad orientation is not delta E, but rather n times delta E. N is of the order of 10 to the 23 in a typical sample. And therefore, that energy advantage is much greater than the thermal energy. The polarization can be of order 1. And so that did seem to be a reasonable solution to the problem. The idea of spontaneously broken spin-orbit symmetry is not a totally trivial one. Next slide, please. Okay, yeah. The ordering is somewhat more subtle than it is in a ferromagnet. In a ferromagnet, in the normal phase, all you're talking about in the case of a ferromagnet is just the atomic spins. In the normal phase, the atomic spins are completely disordered. They're pointing at random. In the ordered phase, they're all lined up along the direction of the external field. So they're all pointing parallel. Now, in liquid helium-3, in the normal phase, if I denote with a red arrow the total spin of a pair, and by a green arrow the relative orbital angular momentum, which is essentially equivalent to the relative position, then what I find is that, first of all, the red arrows are all completely disoriented. They're at random. The green arrows are completely at random. And there's no particular relation between the red and green arrows. But now, in one of the ordered phases, it's actually true of the B phase, not of the A phase, but let's examine that. So in the B phase, what turns out is that, as you see in the bottom right diagram, the red arrows are still completely at random. The green arrows are still completely at random. But you see there's always the same angle between the red and green arrows. And that's the crucial point. And the relative direction of the red and green arrows is actually chosen by this ultra-weak nuclear dipole force. Just in case there are people who would be interested to have a more technical version of this, then for experts only, what happens in the B phase is that for the expectation value of the spin of a Cooper pair is 0, the expectation value of the orbital angular momentum is 0, but there is something which is not 0, which is the cross product, the vector product of L cross S. That's a very delicate property of the B phase. Okay, next slide, please. So, of course, this raises, suppose this explanation is right, you still have to explain what is it that would make all pairs of nuclear spins behave in the same way. And at this point, the existing theory did come up, in some sense, with a possible answer. If Cooper pairs form and undergo Bose condensation, then they must all behave in exactly the same way. And that refers not just to their center of mass motion, but also their internal or relative configuration. So quantitatively at least, the idea that you had Cooper pairing would explain the phenomenon of spontaneously broken spin-orbit symmetry. Now, following I published this summary argument in the fall of 1972, I guess, and that sort of paper attracted some attention, so forth. But I had a heavy teaching load. I was not able to work on that for another 8 months. However, in the spring of 1973, Bob Richardson invited me to go to Cornell for a month. And I spent a month there. I was completely by myself. I had no family at that time. And I could basically spend 16 hours a day just thinking about this problem. And at that point, the last serendipity, number 5, came in. It turned out that you remember that in Kyoto, in my second postdoctoral year, I'd actually worked on two-band superconductors, and that work had apparently gone nowhere. But now it turns out it was precisely a generalization of that work which I needed to do a microscopic theory of the nuclear magnetic resonance in helium-3. And so I was able to evolve a detailed microscopic theory which explained the existing data, and moreover, it predicted a new effect. It predicted that if you did a new kind of experiment where you had it's still an NMR experiment, but now the RF field is actually parallel to the external field, then you would find interesting results. You'd find a finite frequency resonance. Well, at the time, there were no such experiments, but fairly soon later, Davosharov did manage to do that experiment, and it did the theoretical prediction. I should just mention, of course, I was not the only one by any means working on this problem, and in the spring of 1973, there was a very important development, so-called Anderson-Brinkmann theory of the stability of the A phase. It turns out that in naive BCS theory, you would not expect the A phase ever to be stable. But Anderson and Brinkmann were able to show by a very nice argument that in fact, if you went somewhat beyond BCS theory, then you would in fact find the A phase, as we did experimentally. Okay, next slide, please. Okay, so by the summer of 1973, the situation did pretty much seem to have settled down. Both the a priori stability considerations, which Anderson and Brinkmann had developed, and the NMR experimental data, as I'd managed to explain them, both of those were consistent with the hypothesis that indeed both the new phases are Cooper-paired or superfluid phases. In fact, people, from the moment that these new phases were discovered, people started, particularly theorists, started talking about superfluid helium-3. But in fact, it was quite some time before there was any real evidence for superfluidity. However, eventually that evidence was produced, and we do now accept that both the A and the B phases of helium-3 are Cooper-paired and therefore superfluid. And in fact, it turned out, rather surprisingly, that both of these phases had been, in some sense, conjectured before the experimental discovery. BW, that stands for Balian and Wertheimer, although in fact there was a Soviet theorist named Donin who actually got there a little before then, but they were the first in the West to write down that phase. The A phase is the so-called Anderson-Brinkmann Orel phase. Again, had been discussed previously to the experimental discovery. So, as I say, by the summer of 1973, that seemed to be pretty clear. And by the summer of 1974, as I said, you had this longitudinal NMR experiment, which really sort of put the lid on everything. I think nowadays very few people doubt that this identification is correct. So let me finish my discussion by asking, what is superfluid helium-3 good for? Well, first of all, it's the most, well, at the time, I should say at the time it was discussed, it was the most sophisticated physical system of which we can claim details was the most, well, at the time, understand. But you could argue that isn't true nowadays because we have the fractional quantum Hall effect, but at least in those days it was true. And it meant you could predict an enormous number of phenomena, for example, textures, orientational dynamics, topological singularities, a whole lot of things. And some of these things that you could predict and which were experimentally discovered, I should say, they have analogies with systems in particle physics and cosmology and so forth. And one person who's really explored that in great detail is Krishna Bolovic. You can also use superfluid helium-3 to study some aspects of turbulence. And then finally, the application which I like best is the general amplification of ultra-weak effects. Now, one example of that is what we've already seen, namely the NMR. That's precisely a case in which an ultra-weak effect, namely the nuclear dipole-dipole interaction, the effect of that was enormously magnified by the onset of Cooper pairing, or effectively post-condensation of pairs. So let's look for other possible effects. And here is an effect which I predicted theoretically way back in the rather soon after the experimental discovery, in I think the late 70s. And it has to do with that part of the neutral current part of the weak interaction, which violates parity but does not violate time course. The question is, could you see that effect in the occurrence of an electric dipole moment? Well, For a single elementary particle, any electrical dipole moment d has to be proportional to J. That's bigness, Wigner Eckert, still nothing. Um, so, so if d is proportional to J, the total angular momentum, that violates not just parity but also time rules. However, turns out that in the B phase of helium-3, you can actually form the expression L cross S, as we already saw. So your electric dipole moment could be proportional to L cross S, and that then would violate parity, but not time. Your electric dipole moment, next slide, is proportional to L cross S, and so so we just continue this. If you just look at that effect for a single pair, it's just incredibly tight, because remember you're talking about a weak interaction of the elementary particle. It's just incredibly tight. So the rate is going to be, it's just incredibly tiny, hard to see. However, in the B phase of helium-3, all the pairs have the same value of L cross S. And therefore, you multiply that expression by a factor of 10 to the 23. So in other words, you get an electric dipole moment, which is still not large, but it just might be large enough to see experimentally. And if you could see it, that would be rather spectacular. It would be a macroscopic effect of parity violation at the elementary particle level. And so I really think that would be a neat thing if you could see it. In other words, even at the everyday level, you might be able to show that nature does know the right hand from the left hand. Now, as I say, I suggested that way back in the 70s, and at the time, my experimental colleagues looked at it, and they concluded that they didn't quite have the sensitivity to see that. However, it's been 50 years past since then, and experimental sensitivity has increased by many orders of magnitude, and therefore there are people today who are thinking seriously about whether they could actually do that experimentally. I certainly hope that it will be done sometime in the next few years. Okay, so that is what I wanted to say about my work on superfluid helium-3, and I hope I've convinced you that it's not just one happy event, but at least 5 different happy events which are essential in order for me to be able to do this work and eventually get it recognized with the Nobel Prize. Let me just go on to show you 3 more slides. These just have to do with the Nobel Prize itself. Next slide, please. Okay. This is the medal. It's a picture of Alfred Nobel with his dates of birth and death. Next slide, please. Okay. And here are 2 other things. On the left, you have the actual certificate. It's in Swedish, but as you see, it does say that I was given the Nobel Prize. And on the right, you have a little diagram figure. Now, whenever the Nobel Prize is awarded, the committee always asks their artist to draw a little appropriate picture. And this picture is supposed to be a picture of Cooper pairs. It may not be a very accurate picture of Cooper pairs, but it is an attempt to show the general idea. So these are some of the things I got when I was in Stockholm. Okay, so perhaps I can stop at this point, and if there are any questions on the talk, I can perhaps try to deal with them now. And then there's something else I'd like to talk about briefly.
Thanks, Tony. Looks like there's not much on from the audience.
Okay.
Next slide, next slide.
Okay, so then we can go on. Okay, so I'm going to try to talk a little about my experience of lecturing and teaching in Asia. And well, first of all, about my experience with Malaysia. I actually, my first visit to Malaysia was actually way back in 1965 when I was mostly based in Singapore, but with a friend, a Malaysian friend, and we did actually take a trip to Malaysia. We went up the east coast, across the middle of Malaysia, and then back down the Indian Ocean coast. And in those days, that was quite an adventure because there were no bridges over the rivers on the east coast. You had to take ferries, and we had a very broken down old car, which kept on breaking down, and so it was not at all trivial to get around like that. And in fact, I remember one point we actually managed to break down rather badly. We sort of stuck. In fact, I think we were stuck in a sort of field of mud. But luckily, it turned out we'd broken down exactly in front of the local middle school, and the headmaster saw our problem, and he brought out all the students of this middle school to help push us out of the pothole. So it was quite an interesting experience. Then, of course, much more recently, I had this very nice experience at UNIMAP in 2013 when I gave a lecture and was awarded a honorary degree and so on. And that was very pleasant indeed. Um, Next slide, please. Yeah. Um, this will be, I think is um, Singapore, isn't it? Yeah, I think so. Or is this still Unimap? Perhaps we should go on to the next one because I'm afraid I can't always identify where these are. Yeah, okay. So Singapore, well, as I say, I spent 3 weeks in 1965 or so, in 1965. And then I resumed my contact with Singapore from about 2000. And over the next decade or so, I had annual visits. I was on the um, International Advisory Board of the Physics Department of the National University of Singapore. I was on the board of the Centre for Quantum Technology when it was set up, and I gave lectures at the ISYF or GISS as it became. And so those are pictures from that experience. Next slide, please. Um, yeah, that would be, I think, still Singapore, in fact. Yeah. Next slide, please. Yeah. Okay. So in Japan, I have a considerable experience. I spent the academic year, as I already mentioned, from 1965 to 6 in Kyoto. And then, shortly after my work on superfluid helium, well, when I was still continuing my work on superfluid helium-3, spent another year in Tokyo in Professor Yasushi Wada's group. And I had many short visits between over the last 50 years or so, and there's many contacts in Japan. And one person who was particularly involved in my research on superfluid helium-3 was Shin Takagi, and he is the person on the right there in the middle photograph. Here. So, as I say, he was extremely helpful in the later part of my work on superfluid helium-3. Okay, next slide, please. Yeah. So China spent um, for a period between about 2014 and 2019, spent a summer period at Shanghai Jiaotong University, initially 1 month, subsequently 2 months. Um, and you see a picture with, well, um, President Xi Jinping and various other people there. I met him just once for a very brief period. I I should say I tried to exchange brief remarks with um, President Xi, but unfortunately my Putonghua, my Mandarin, was not up to it, and so he just said ni hao. That was it. Okay, next slide, please. Okay. And yeah, India. I've been to India many times actually, but always for rather short visits. But the place I've particularly visited is Kharagpur, where I did have an ongoing collaboration for quite some time, and visited there I think three or four times over the years. Um, and then I should say that there was a very nice celebration of my 80th birthday. That was actually in Bangalore in 2009, the spring of 2019, in fact. And finally, yeah, I think this is the last slide of these. Next slide, please. Yeah. And finally, I had various visits to Taiwan, Korea, Iran, and here are a couple of photos from my stay in Iran. I went with um, with Professor Paul Chu, who is the second from the left in the dinner photo there, and with Professor Warren Pickett, who's sitting next to him to the right there. So that was in 2014. That was a very interesting experience indeed. Um, so um, so I was asked just to say a few words about my um, what I would conclude from my experiences of work in Asia, and particularly about um, the the requirements or the possibilities of setting up institutes of advanced science. I did try. I was involved in setting up such an institute in China at SJTU when I was there. It wasn't all that successful, but at least one could see um, what are the important points to note. And so I would basically say something like this. Um, First of all, I think if you're going to set up an institute of advanced science, particularly in a relatively small university or in a country which is not one of the major players in physics, then you probably should try to choose a relatively compact subject area. And in fact, in the case of SJTU, we actually chose the area of the intersection between condensed matter physics and quantum information. When we actually started this institute in, I think, 2014, um, that seemed to be a rather new field, and there were not too many people working actively in it. Of course, by now, 10 years later, there are lots and lots of people working in it. So I think we, in some sense, chose rather well. But I think in some sense, it's probably, if you don't have a very a large amount of money for your institute and you therefore can't employ too many people, it's probably best to choose a field which is not too hot at the time you start, because you don't want to be competing with all the places which have lots and lots of money, like Stanford or MIT or whatever. So find an area of physics which is interesting, but not at the moment all that hot. And for example, one might think, for example, about the physics of certain kinds of insulators for that. Then you have to think a little about the conditions of employment. Are you going to make people permanent members or have a limited term of membership, which could perhaps be renewed. If you're going to have a limited term membership subject to renewal, then I think it's important that if the appointment is not renewed, the person in question can just revert to being an ordinary faculty member of the university. So it's important they have something to, as it were, fall back on or go back to. Um, you don't want people to be continually thinking about how to find their next job and so forth. If, on the other hand, you're going to make employment in the institute permanent, then what you do, I think you want to watch out for your age distribution. It's a great temptation when you set up a new institute to stock it entirely with the brightest young people who are on the market. And I think that's a mistake, because those people are going to go through the system together, and 20 or 30 years later, they're all going to be at the same level. Some of them will have done very outstanding work. Others probably won't, statistically speaking, but they'll still be, as it were, blocking the system for new hires. So you don't really want that. What you want to do is to start with a sort of more uniform distribution of age, so that people are continually leaving the institute. You can put in others at the bottom end. One thing that I think is sort of obvious in a way, but I found was actually rather important in Shanghai, and actually was, I'm afraid, one of the reasons we didn't succeed very well, is the question of international applicants. We advertised our institute quite extensively, and we got a lot of applicants from not just from China, but also from the US, from Europe, from Japan. And the international applicants were almost always worried about one thing, which is schools. They usually wanted to send their children to some kind of international school, but unfortunately, these international schools are usually pretty expensive, and therefore, we really needed extra financial incentives to cope with that. And for one reason or another, SJTU couldn't really come up with that adequately, and therefore we lost a lot of people because of this consideration. And finally, I think it's very important. You want to be able to give younger workers a chance to relax. One of the things that I think really rather depressed me in China, and I hope it's in some sense, well, it's certainly not unique to China. It happens also in the US and other places. I hope not in Malaysia, but I don't know. One thing which I found in China was that from very, very early on, the enormous short-term pressure on people, not just to publish papers, but to publish papers in so-called high-impact journals like Nature or Science or PNAS. Um, and moreover, to publish it over the time scale of a typical PhD or postdoc. And that's typically 2 or 3 years. Now, you do not want your people always to be thinking about what they can publish within 2 or 3 years. If you do that, then almost by definition, they're not really going to be addressing the really important problems. They'll be looking for problems which can be guaranteed to give a solution within that short time scale. And so almost by definition, those are not important problems. So somehow you've got to find a way of allowing people an extended time scale to do their research. So a minimum of 5 years, but if you can do better than that, well, do it. And I think those are some of the conclusions I would draw. Thank you.
Thanks,
Thank you.
Prof. Tony. There was some journey there, a lot of serendipities. That there is one question in Zoom by Park Chen, similar
Okay.
to one I wanted to ask.
Okay.
Um, One, with hindsight, do you think it is possible for you to make the same scientific discoveries that you have made without the serendipity?
Um, Probably not, to be honest. Um, no, I think um, one as I mentioned, one thing which is very, very important was the things that I did not know. Um, and in particular, as I mentioned, um, had I known the standard theory of NMR, almost certainly I would not have done the work I did. Because having to start off from scratch was, in retrospect, an enormous advantage in that case.
May I ask what was the reason that you did not look into NMR when you said your colleagues were all familiar with it?
Yeah, good question. Well, I took one look at Abragham's textbook, which is about this thick, and I thought, look, by the time I finished reading Abraham and totally familiarized myself with standard MR theory, the whole problem is going to be cleaned up. So
Right.
there's no point in starting.
Okay.
I should also, one other comment I'd like to make, which is connected with what I was saying right at the end. I think I would never have been able to do this work had I been in the position which most people are in um, at my level. You have to remember, we're talking about, let me think, we're talking about the early 1970s, when I was a junior faculty member at the University of Sussex. And basically, I had tenure there. Um, and as I perceived it at least, my job at the University of Sussex was teaching. If I did a good job teaching for the week, then on Friday evening I could go home and think I'd earned my salary. And if I then wanted to spend the weekend doing research, well, the university would support me. They'd give me adequate library facilities. They'd give me secretarial help, and so on and so forth. It was not part of my job. Research was not part of my job. Um, and I think that was an enormous advantage and enabled me to really relax and think about things um, in a leisurely kind of way. I was not in the kind of position that most people are at today in the US and even more in China. You know, have to publish two or three papers in Science or Nature or PNAS by the time you need to apply for your next position. That's awful. I would
Uh,
really like to do something about that.
I would like to take up an argument on that with you. Comparing the total the rate of production of impactful papers of US compared to China. Obviously, clearly China is has taken a big lead right now, and I would in a limited way I would like to say that that they are moving forwards technologically. But my question is, does that really bring about to the crux of the question that you put up of the fundamentals of things?
Well, no, I think at least in certain areas, technological advancement does does it more or less directly intersect with fundamental research. I mean, in the history of physics, if I can just digress for 1 minute, in the history of physics, you saw that the whole science of thermodynamics really came out of practical engineering problems in the early 19th century. Um, and in the same way, trying to develop, for example, quantum communication at long distances has put demands on fundamental understanding um, of, um, of concepts of quantum information. Um, in fact, in some ways, I think there's been an enormous cross fertilization between traditional problems in the foundations of quantum mechanics and the kinds of problems which have been flung up in the quantum information field. And as I say, those problems have, in many cases, been the direct, almost direct result of what are now the modern engineering problems, like say secure and principal communications stuff. So yeah, and so at least in certain areas, I think there's a very direct connection, and I don't doubt that China will continue to produce not just good technological work, but good fundamental work in that kind of area. Of course, there are other areas where that's not necessarily the case, or not the case right now, but in some important ones it is.
That I would like to go back to Park Shen's question, number two, uh, on advice to current graduate students and early career researchers on how to pursue an academic path in the current academia.
Okay. Well, okay. I mean, that's a question, of course, which I tend to get asked quite frequently. So I have developed a pretty um, standard reply to it. I would say perhaps the most important thing is to follow your own curiosity. Um, if there's a question which intrigues you and you don't feel it has been adequately answered in the literature, then spend some time thinking about it. And don't worry if people around you say, oh, that's a silly question, everyone knows the answer to that. I mean, I always quote in this context the case of Einstein. Um, when uh, when Einstein started to think about it, there'd been something like what 300 years since Galileo, and everyone had just assumed that in vacuum, every object, independent of its composition, its shape, its size, whatever, every object would fall with the same acceleration, with old g. Um, Einstein asked why. Um, and I'm sure that when he asked that question, a lot of his colleagues said, oh, that's a stupid question. I mean, everyone knows they just do. You know? But Einstein um, did work away at it, and eventually, of course, that's what led to general relativity, which is, I think, perhaps the most beautiful part of modern physics. So that's the first thing, and follow your own curiosity. Secondly, don't worry um, too much about whether the question you're thinking about has been solved in the literature or not. Um, if you covered it from scratch, um, almost certainly you'll learn something. And even if it turns out, at the end of the day, you may come up with a solution, then you can go to the literature, you find out that, well, someone actually had a paper 50 years ago which actually did that. Don't worry. Um, your work was not wasted. Right? So I say, don't worry too much about just about reading all the literature that there is on the subject. Again, I've used that principle several times in my career. I just said, forget about the literature, just go ahead and do it. Thirdly, um, um, don't feel any piece of honestly done work is ever wasted. Even if you feel it's gone nowhere, don't worry. Write it up. Um, Write it up carefully. That's important. Write it up carefully. Put it away in a drawer. I would bet that 10 or 15 years down the road, it's going to come back and help you out. Again, you see, that was the case, in my case, with the Kyoto work on two-band superconductors. At the time, it seemed to be a complete waste of time. But in the end, it turned out to be a key to a more important problem. Um, Fourthly, keep things simple. Um, don't don't get too fascinated by um, heavy formal methods. When I was a student in Oxford, and we're now talking about the late 60s of the last, well, actually the early 60s of the last century, most of us got um, fascinated by the Green's function techniques, which at that time were very new. They were coming out of Russia and out of Japan, and we actually got a head start on this because our advisor was Dictor Haar, and he was the editor of some of the Russian journals, so translation journals from the Russian. So so we knew all about these fancy methods of Green's functions and so forth. And in fact, I didn't mention this because there's too much detail, but when I was looking at the original problem in Illinois, that is the problem of combining um, BCS theory and Fermi liquid theory, my first thought was to go at it using these Green's function methods. And in fact, I did. And it was only after I got a puzzling result that I said to myself, well, okay, this is fine, but I really want to understand this. Where does this puzzling result come from? It really isn't possible just to stare at the Green's function and find that out. So I was able, in fact, to formulate a much more intuitive way, is what I call um, the method of generalized molecular fields. I found a way of reformulating Landau-Fermi liquid theory in such a way as to apply it to the superfluid phase. Um, and it was only when I got that very simple, intuitive picture that I really believed my result, the result I got by Green's function. So if you can forget about the Green's functions, forget about the functional integrals, try to formulate things in as straightforward terms as possible. And then finally, one fifth principle, which I think is perhaps in some ways the most important of the lot. If your job is a job, as in fact, for most people it probably will be, it's a job which involves not only research but also teaching. Now, take your teaching at least as seriously as you take your research. That's going to be good, not just for your students, it'll also be good for you. Some of my most important ideas in my career have actually come out of my teaching activities. So I think that really is very, very important. Okay, so that was what I said.
Thanks, Tony. There's another question in the chat. Tony, the A and B phases of superfluid helium-3 exhibit spontaneous symmetry breaking similar to early universe, breaking similarity to early universe phase transitions. Have there been any experimental developments that strengthen this analogy?
Yeah, I would have to say, quite frankly, I'm a little skeptical about the business of making too making too much of the analogies between condensed matter physics and, for example, cosmology or particle physics. Um, the thing is, if you suppose that you one example of this, for example, would be the Kibble-Zurek mechanism. Um, Kibble produced this idea that in the early universe, um, these symmetry would be broken spontaneously in different ways in different regions of the universe. And when they started to combine, um, they then they wouldn't always meet up, and therefore you get singularities form. You get these cosmic strings. And then Zurich had the idea that maybe you could make an analogy for that in liquid helium. And I mean, I actually think that the work that Zurich did on that was very valuable for research on liquid helium. I don't really think it was terribly valuable for research on cosmology, because after all, the problem is that if you get a result which basically the analogy is that the the theoretical structure looks at first sight the same in the two cases. And at a very basic level, it probably is. But now you go and do the experiments, and you find out really that the experiments don't agree terribly well. In fact, I mean, of course, there have been a lot of experiments on the Kibble-Zurek mechanism, and um, Some of them have seemed to have agreed with the original predictions, but others haven't. And in particular, Zurich suggested experiments on a particular system, namely liquid superfluid helium-4. The original experiments on superfluid helium-4 did seem to agree reasonably well with with Zurich's theory. However, subsequent experiments have not agreed at all well. And you see that's not unnatural because it turns out that there really are considerations in liquid helium, for example, considerations regarding the thermal conductivity and so forth, which really don't have an obvious analogy in the early universe. So basically, if the systems come out the same, well, if the experiments come out as predicted, then you say, well, the theoretical structure is indeed relatively the same. If they come out differently, you can always find an explanation in the physical differences between the systems in question. So I'm not that fascinated with these analogies, but I would have to say that they have suggested experiments on condensed matter systems which are valuable in their own right. And so, from that point of view, they're certainly not a waste of time.
All right, but aren't they both uh, based on helium? Of course, the universe doesn't specify whether it's helium-3 or helium-4, but helium generally.
Yeah. Well, as I say, the, I mean, I think what's slightly ironical is that, as I say, Zurich did originally suggest helium-4. Um, Helium-4 has not worked out too well. However, that had he not suggested helium-4, I don't think people would have been interested in doing experiments on other things like say, superconductors or magnetic systems. Some of those experiments do seem to have worked out rather well, in rather good agreement with the original theory. Now, in the case of helium-3, I think there's still a big question mark there because in the case of helium-3, you have the prediction of the generation of vortex lines. I don't actually think that the agreement of experimental theory there is all that impressive. In particular, there's one experiment from I guess this is the Lancaster Grenoble group way back. It's way back. We're talking about the late 90s, something like that. Um, was the this experiment, which was basically thermal um, in nature, which claimed to verify the Kibble-Zurich theory of generation of vortex lines in superfluid helium-3. But they okay, there was a direct experiment from Helsinki, which did actually measure the vortex lines themselves, and I think that was reasonably convincing. There was another experiment from at the same time from Lancaster and Grenoble, which claimed to get evidence for the Kibble-Zurich mechanism, but it was evidence from what's the word? Not thermal, but basically from considerations of the heat balance. Um, there was some unexplained sink of heat, and they tried to uh, um, they tried to explain this this sink by the formation of vortex lines. And they claim this then agreed with the Kibble-Zurich theory. I think that was a very dubious experiment because there are all these things. Because what they'd done was basically to irradiate helium-3 with fast ions. Now, people have done those experiments on helium-4 for many years, and they know that if you irradiate helium-4 with fast ions, you generate a whole lot of stuff. And one of the things you generate is these long-lived metastable molecular, quasi-molecular complexes. It's a complex of a helium ion and a neutral helium atom. So it's a dimer, basically. It's excited state. It locks up something like 18 electron volts of energy, and it stays there for 10 or 15 minutes. And so I think that in that particular experiment, much of the energy deficit which they saw was due to creation of these molecular ions. I tried to persuade the experimentalists to redo the experiments, but they had other things to do, so I didn't do it.
It's interesting. On helium three, Tony, what 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 are the conditions in helium three besides the um, lack of one nucleus component? What else causes the precession and stuff? Why helium three in that sense?
Uh, well, okay, I'm not quite sure I understand the question. I mean, the helium-3 nucleus, of course, is composed of two protons and a neutron, and so they can't d- um, they can't form zero spin as helium-4 does. So you must have a nuclear magnetic moment. And borrowing pathology, that nuclear moment is not going to be zero. So it is natural that it will process around the magnetic field. Did I understand your question correctly?
Yep, you did. Yep, you did. Yeah,
Okay.
correct. So it's the nuclear alignment.
Yeah, I mean it could have been, I suppose, that somehow the protons and the neutron just conspired to give you a total magnetic moment of zero, but that would have been a very pathological situation.
Okay, okay. So in that sense, in your SBS SOS uh, 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 slide, when you talk about polarization, you are talking alignment of electrons or the atoms themselves.
No, no. Okay. So one thing is very important to remember is that under the conditions where the liquid helium-3 is stable and in thermal equilibrium, the electrons are basically doing nothing. I mean, the electrons are the helium atom, whatever isotope we're talking about. The helium atom has two electrons. They're both sitting in the 1s state. They're doing nothing. They're not contributing a spin because their spins are opposed. They're not contributing an orbital angular momentum. They're in an S state. And so what you're talking about is the nuclear spins and the orbital angular momentum of the two um, atoms as a whole. If you like, you could even say the orbital motion of the two nuclei accompanied with their two s electrons around one another. So that's what SBSOS is about. So like I said, the spins could be, they could sit either like that, which is good, or like that, which is bad. It would be more accurate to say they can rotate around one another, either like this, which is bad, or like this, which is good.
Okay. In chat, Cooper pairs exhibit macroscopic quantum coherence. How do you see this property being leveraged in future quantum technologies such as quantum computing?
Well, um, I think the most promising way, although it's all that not all that promising by comparison with other systems, would be to exploit the fact that helium-3, the A phase of helium-3, is what we call a topological Fermi superfluid. Um, that describes a particular property of the wave function. In this case, it's mostly the orbital wave function you're talking about. It's a so-called P plus IP state. That means you have a non-zero angular momentum, and moreover, and that means in turn that the system is not not invariant under time reversal. So that's a very peculiar kind of state. Um, yeah, it turns out, there's a lot of theory which goes into this, but it turns out that in that kind of topological Fermi superfluid, you can have or it's believed, I should say it's believed that you could have a particular kind of elementary excitation, um, so-called Majorana fermion. And in some sense, a Majorana fermion is like half an ordinary fermion. And it has very peculiar properties. And in particular, um, if you can manage to braid these Majorana fermions, it is predicted theoretically that you can carry out topologically protected quantum computing. Now, lots and lots of theorists have worked on that. Um, there have been a lot of experiments to, as a matter of fact, mostly not in helium-3. Most of them are in certain kinds of superconductor. But there have been some experiments on helium-3 which have claimed to find, to experimentally find these Majorana fermions. Right now, I think there's a lot of doubt and confusion about that. There's a particular person, Sergei Frolov, he was actually a postdoc at Illinois some years ago, but he's made a study, a rather careful study of the various experiments which have claimed to show Majorana fermions. And his conclusion, at least until recently, was that really none of these experiments are convincing. And I myself believe, and this is a very complicated technical issue, but I myself believe that the theory is actually not adequate. That that these Majorana fermions may be a sort of science fiction. They don't really exist in nature in real life. That's an important question, a very important question, and I'm certainly trying to encourage um, more experiments and more theory on that.
Okay. All right. Thanks, Tony. One last one. On a personal level, how helpful were your dual degrees in your journey?
I think okay, you're talking about my first degree, which was in the Oxford Grace course, which is partly classical languages and literature and partly ancient history and philosophy. Yes. I think I don't think either the languages and literature nor the ancient history were directly relevant. I mean, they're very interesting, and I'm very glad I did them, but they weren't directly relevant. The philosophy, on the other hand, was relevant. I don't think it's helped with so much with specific problems in physics, but it's just led me to a generally much more skeptical attitude than I think many of my colleagues have. Um, I mean, philosophers are always asking two questions. The first question is, what do you mean? And the second question is, how do you know? And I think, by and large, I find my physics colleagues don't ask these questions enough. um, you need to you need to discuss carefully, particularly when you're on the edge of your theoretical understanding. You need to ask very carefully what exactly you mean by, say, I don't know, saying that such an effect is non-local or whatever. Um, just relatively trivial things like that. And then you need to ask, how do you know? In many cases, I find that my theoretical colleagues quote things with extreme confidence. And when I ask, how do you know? They refer me to more theory. Well, I think that doesn't satisfy me. I want to know what are the experiments which show this result.
Mm.
And so that is very important again. So I think this instead of skeptical attitude has been very helpful. But as I say, I don't regret any of my my first degree. I think it was I really would not have sacrificed it for anything.
Okay, okay. One last question from Dr. Sharifah. Thank you for your answer, Tony. Can I ask one? I would like to know your opinion on this. Physics relies on deep intuition and conceptual breakthroughs, yet AI excels in pattern recognition and computation. Do you think AI will ever contribute to fundamental theoretical discoveries, or is human intuition irreplaceable?
Um, yeah, I would like to believe that there is something peculiar about human intuition, which AI is not going to be able to replicate. However, I would have to admit that, if you'd asked me, or if you asked most people, I think, way back in, I don't know, say 1980, whether AI was ever going to be able to do the things which is now routinely doing, most people would bet very heavily against it. So, so I have to say we have underestimated it in the past. We may be underestimating it in the future, but well, as I say, I would like to believe that human beings are still unique.
I concur on that. I would like to believe so too.
Yeah.
Okay, with that, we have come to the end of our session with Prof. Tony, Sir Anthony. Um, Thank you for bringing us very much into the world of low temperatures and serendipities of life. Um, Before we spin our good day to you, please stay on for a picture session. We'd like to take pictures with everybody. And as such, please, all the attendees, could you please switch on your cameras, please? Thank you. Cameras, please.
Um,
Thank you.
okay.
I saw Dr. Hashima somewhere. Good evening, doctor. Cameras, the back pages, the cameras are not on. Most cameras are off. Please, everybody, cameras. Cameras, 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 cameras. Cameras, please. Back pages, cameras are all off. Cameras, cameras, cameras. Come on. I think that should do it then. Okay. Thank you, Tony. Have a good day.
Thank
Hope
you.
you sort out
You too.
uh,
Yes. Yes.
personally. All right. Thanks for
Thank
your talk.
you.
Hope we could engage you for further such interventions into our physics.
Certainly. Certainly. Yes. All right.
Thank you very much. Thank you very much.
Okay.
Nazri will contact you later with the certificate.
Okay.
Yeah. Okay. Thanks, Tony.
Okay. Bye-bye. Okay.
Bye-bye.
Right.
Let's see.
For other attendees, the QR code is displayed. Please, that's for Unimap, and you can also fill up your in the chat session. There is the attendance link provided. It's a Google form. Please. Thank you for attending, and goodbye. Till we meet again, Series 22.
Recording stopped.